step up over there. One for everybody.
All right.
Oh.
Over.
Yep.
All right, are we live?
I think so.
All right. Hello, Internet. Hello, kittens. I believe there's a lot of kittens on the Internet, so hi, kittens.
Yeah.
This is Papers We Love. Oh, puppies too?
Yep.
Wow, the Internet has everything, doesn't it?
And furries.
Oh, and furries. Oops. Wrong meetup. So this is Papers We Love San Diego. Thanks for coming in here or at home or at a future date, anywhere. So I'm going to keep this real quick. We are now live streaming, as you might know. That's announcement number one. Announcement number two is we have a list of papers now that you can find on our Meetup page or on our Slack channel. And these are papers that are basically recommendations or suggestions if you think you want to present, but you're not really sure what you want to present. We've heard a few people say that. Well, now we have a list of papers that you can, with confidence, pick one and present it, and everyone will be happy. Or if you just wanted some ideas, there's plenty of ideas here. There's a lot of historical kind of seminal papers there. That's kind of the skew of this list. But you don't have to do that. There's some newer ones too, and the beauty of it is you can add papers to this list. If you don't want to speak, but you want to see a paper presented, you can go in here and add your own paper. And then maybe someone else will pick up the paper and run with it. We're looking for a speaker for next month. That's September. Oh, all right. Yay, we got
All right.
All right,
fast.
so Roger will be speaking. Do you have a paper picked out?
Well, there's a list I can pick out.
Okay.
I have a particular one.
All right.
Okay, perfect. Let us know, and then, not too distant future when you pick one, and then we'll make sure to get everything posted. But that'll be great. Looking forward to it.
I forgot her name, but she'll be back next section. Lisa?
Lisa, yeah.
Lisa. She contributed some of those documents, right?
Yes.
Mm-hmm.
So some, she taught a course on, I'm not sure exactly what it was, but it included a list of seminal computer science papers that she put together from various sources. I think other professors who had taught similar classes, and then she kind of got them all together and then gave us this list. So half is from there, and half is from Carnegie Mellon's list of seminal computer science papers. And then please add more, so it's not just those two sources. Perfect. All right, well then, without further ado, we have a great speaker today, Valentin Robert.
Mm-hmm.
And he is a grad student at UCSD. And please, what? Oh.
In computer science, in verification of software and programming languages.
Who are your advisors, curiosity?
Sorin Lerner is my advisor. And in Europe we also have Ranjit Jala.
All right.
And also, I forgot we were going to specify earlier that please just clarifying questions during the talk, and then we can kind of dig into everything after the talk.
And if anybody has questions who might be watching online, go ahead and ask them, and we'll I'll raise my hand over here.
Perfect.
Can we take like a half a minute for you to describe what work you're working on? Because every grad student is working on something cool, right?
I can start with that, yeah.
All right, well, here we go.
Thank you.
Well, please let's do the warm welcome.
So, hi everyone, I'm Valentin, you can call me Valentin, it's fine. As we just said, I'm a PhD student in computer science at UCSD, and I work in the field of programming languages, and in particular more on software verification using proof assistance and languages with dependent types. So in particular, what I'm looking at these days is how to repair verified programs when a user is changing them, so sort of refactoring but adapted to programs that have proofs. Well, the idea is that if you've already verified a program but you start changing bits and pieces of it, there are some mechanized ways of updating the rest of the program and the proofs about this program in such a way that you can sort of like do a lot of the work for the user without having them type the boring tedium parts of it, and then they're just left with like obligations that actually have changed and need more human brain or something like that. But I'm trying to ease this process by automating whatever I can out of this.
Cool.
And so I picked this paper because it's one of the seminal papers in my field, in fact. So it's this, I think, 1969 paper from Floyd-Hoare called An Axiomatic Basis for Computer Programming. And so just to say a little bit of context about 1969, that was a long time ago, I think. At the time, the languages that people were using were those Fortran, Lisp, Algol, BASIC.
And assembly.
And?
Assembly.
Oh, of course, yeah. And so, I mean, it was basically the very premises of functional programming, procedural programming, and sort of like structured programming was getting really more and more popular. But there was no C yet, no Prolog yet, no ML yet. They were like just about to be created, I guess. Linus Torvalds was also just about to be created, for instance. And the internet back in the days looked like this. So it's a very early time in programming, but not quite so early that...
Wasn't Chicago in there?
Maybe, I don't know, I got this from the internet.
Probably.
Could be wrong, could be a
Probably.
dog or a cat posting fake maps. But yeah, so at this time, Floyd-Hoare was starting to think about programs, and he was wondering how he could prove certain properties of the programs that people were writing in those procedural languages. And so his idea was that, okay, he wanted to avoid basically this, which is what happened when I was preparing this talk, to avoid certain kinds of bugs in our program. So we would like to be able to prove certain things. And so his starting point was that the execution of a program at this time was an exact science. You have instructions and they always do the same thing. There's not any sort of probabilistic thing going on. So at the time, basically, you should be able to figure out what a program does. And as a result, you should be able to reason about what it does. And to help this reasoning, he was taking the idea that, well, in the same way that in order to reason about mathematical constructs, we build systems with axioms and rules to sort of derive different properties about certain systems by using these axioms and rules. He wanted to have the same kind of ideas just for programs. So he wanted to have a set of axioms and rules that he could use to reason about the kind of programs that people were writing at the time. And so we're going to see what those axioms and rules that he came up with initially were, and then what happened since this paper was published. So I guess one of his starting points was like, well, let's see what happens when we just start writing some arithmetic operations. So that's like the first part of the paper. And he's already considering that this is not quite so easy as one would think. So he starts saying, well, we probably want to reason about some sort of arithmetic. And so, for instance, we might want to postulate the axiom that x plus y should always be the same, or y plus x should be able to swap those. And for most intents and purposes, I think this would be true. So sure, we could accept that. But then he started thinking about, well, what about x plus 1 is always greater than x? Well, maybe that's true for real numbers, but when you have integer arithmetic on computers, there might be either overflows where x plus 1 is actually lesser than x, or there might be just top bounds where at some point x plus 1 reaches a maximum value and just stays equal to x. So even at an axiom like x plus 1 greater than x is already something to ponder and to depending on whether you want to capture the real arithmetic meaning of a program or whether you want to capture what's actually happening in the bits in the machine. So that was already something. And then if you start thinking even about this kind of thing, which I think for most operations would be true, but once you start thinking about floating point numbers, this is also something that might actually not be true. So already arithmetic was like something a little shaky, but it sort of eventually settles down on a bunch of axiom for computer arithmetic that he wants to use. And then he moves on this paper. So when you design a system, there's a sort of like choice you have to make here, but then what's interesting is more reasoning about programs that are composed of multiple operations and different things going on. So then he started wondering, well, what are the rules to reason about a program that's more than just one equation or one assignment or one test? So the problem about programs at the time were basically sequences of instructions. And so what we want to know is at different time in the execution of a program, we want to be able to say something about certain variables value or something like that. So he wanted a way of reason about different times of the execution of a program and be able to say things about variables at this time. And so it wasn't necessarily the case that you should always be able to say, well, here x will definitely be equal to 3 or here to 5. But it might be you want some sort of more relational way of describing the program. We want to say, oh, well, this variable will definitely be greater than that variable. I don't know the exact values, but I know that whatever the values are, they satisfy this relationship. So we want to be able to say things, I don't know, like x must be the same as y plus 1, which is a relation between x and y, but it doesn't really concretely say what x and y will be, because they could be many things. And so we started reasoning about how to set up rules to make this happen. And so I think I have a little small example to start thinking, how would we reason about a program? So this is a kind of like neat way of swapping two variables in place without really having a third variable. It's not that useful these days. It's just interesting. If you only had two registers, then it might be the only way you could swap two values using two registers. But nowadays, your compiler will probably do something better than this anyway. But let's see about how we would convince ourselves that this actually swaps the values of x and y. Well, one way we would start going is maybe saying, well, at the beginning of the program, x must have some value, and I'm going to call it x0, and y must have some value, I'm going to call it y0. And then I'm going to, in my head, evaluate each step and try to like update this knowledge that I have about those variables. So once we execute, so okay, when I use this colon equal syntax, that means an assignment. It just made look different than equal, where it's going to be more the logical equality between two things. Colon equals, just think of it as assign the right expression to the left variable. So when we run the first assignment, well, y is going to receive whatever the value of x plus y at that moment was. And since x was equal to x0 and y was equal to y0, I would expect that x still is equal to x0 and that y must be equal to y0 plus x0. And I can keep going like this, updating my knowledge based on what I knew before. So after executing the next statement, it should be the case that now x becomes equal to the current value of y minus the current value of x. And if you do the math with the things on the right, you'll see that the two x0s cancel out and you only get y0 in x, and y hasn't been updated. And then after the last execution, after the last statement, x doesn't get modified, and y receives the current value of y minus the current value of x, where the y's cancel out, and y is equal to x0. And so this maybe convinces you that somehow we started where x was equal to some value x0, and at the end x is equal to y0, and vice versa for y.
Well, speaking to your earlier slides, only if these are integers and only if overflow does not occur.
Exactly, yeah. So yeah, I'm setting apart those valid concerns about overflows and things like that. So yeah, assuming that this is all just, let's say, real arithmetic or...
And especially integers.
Oh, sorry, yeah. Either integer arithmetic, or actually, yeah, real arithmetic and not floating point arithmetic. But yeah, assuming that we have axioms that I've been using to cancel out those computations, then we should believe that this program satisfies this sort of sequence of deductions. And so I try to set up the rules that would let us actually derive formally these kinds of deductions. So you've seen what I've been doing is that every time there was something that I knew before executing one instruction, and then after the instruction I was deriving a new set of things that I knew about. And so you wanted to capture this using like a concise notation. And so the notation that he uses is this notation PSQ with certain curly braces. Actually, if you read the original paper, he uses a notation that's a little bit different, where the S is within the curly braces and P and Q are outside the curly braces. But since then, almost the entire research community has changed to this notation. So I updated the notations to what's being used those days. And so formally what this assertion says is that it is true only when executing in a state that satisfies P, which I will refer to as a precondition. When you execute the statement S, and if it terminates, which will become interesting later, then you should end in a state that satisfies the post condition, as we call it, Q. And so this is what I will refer to as a Hoare triple, but a lot of people want to call it rather a Floyd-Hoare triple, because Floyd at the same time, or like even a couple years before, wrote a paper that really set up some foundation for this. So this thing, I will call it a Floyd-Hoare triple or a Hoare triple when I'm being lazy. And so I'm going to give you a couple examples to see like what they would look like. So here, for instance, is this for triple says that, or if I were to start in a state where x is equal to 41, and I were to run this statement where x receives x plus 1, assuming the statement terminates, which it should, I should end up in a state where x is equal to 42. So this, I think, you would agree that it's probably true. Again, barring any sort of like architecture where you only have values up to 41, or I don't know. Here's another example where it says, here the precondition is just says true, which is a way of saying that we don't really have any precondition. Like, regardless of what the state is, in any state, if you were to run an assignment of x to 0, you should end up in a state where x is equal to 0. Now, whenever I'm going to have like a bigger program in between these two pre and post condition, I might write it vertically like this. And here it says that if I start in a state where b is true and a is 21, and I run this little program, I'm going to end up in a state where x is equal to minus 21. In particular, you might notice that I'm not necessarily saying all the facts that we know at the end. For instance, I'm not saying what happened to b and a in the post condition. And so we'll see there that there are certain things, there are certain triples that may be valid or not valid, and certain that may be precise or less precise. So for example, I'm going to two examples that are more shaky. Here's an invalid triple, for instance. I can write that if I start in a state where x is 41 and I increase x by 1, x is equal to 23. This is not true. So whatever formal system we build, it should not let me derive this from the axiom then rules. I mean, assuming that I don't want this to be true, but you would probably assume that you or agree that I don't want this to be true. And now some triples might be imprecise in the sense that they are true, but they might not tell us everything about what happened. So for instance, this triple that says, if I start in a state where x is 41 and I increase x by 1, I end up in a state where x is greater than 23. Well, that's certainly true, but maybe I could be more precise and actually tell you that x is going to be definitely equal to 42. So there are certain triples that are valid but not precise. And so we're going to want a way to figure out which ones are valid and derive from already things that we know valid, more valid things, and not be able to derive invalid things. Yes?
So valid is always precise.
No. For instance, this one is valid in that it is true.
Okay.
But it is not precise in that the post condition tells us a vague fact about x, whereas it could tell us a stronger fact about it.
So it can be valid and imprecise.
It could be valid and imprecise. And if it's invalid, I guess we don't care about precision because it's invalid in the first place. But I guess it could, yeah, it wouldn't really make sense in that case. Okay? Yeah, that's a good question. And so yeah, how do we tell when we are giving like precise specifications or loose specifications? So to start with, like, I'm gonna start with the first axiom that he builds, and I'm gonna have you sort of like guess what this axiom should look like. So let's try to see what an axiom for the assignment operation should look like. So
could we go back to the previous slide?
Yeah.
So on the some triples are imprecise. At
Mhm.
the very end of that, x is greater than 23.
yeah,
If we say x is greater than 23.2 point blah 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 blah, many decimal points behind that, which would give the perception of some kind of precision,
mm-hmm.
it's clearly imprecise,
yeah,
which is telling me that there are two different types of precision. You know, for example, how precise is that 23?
mm-hmm.
As a number, is it exactly that, or is it actually point blah blah blah,
Mhm.
many decimal numbers, versus the in context. So the 23 by itself is not very precise. Yeah, only two decimal places. But the real imprecision you're talking about is the context. So
Yes.
I'm just feeling two types of precisions here. Yeah,
I am definitely talking about the second one and not the first one. So here, for instance, if we were in a setting where x is an integer and not any sort of real or floating point value, then I would consider that 23 is, I mean, it's a precise value. There could be an imprecision if you were talking, for instance, in terms of floating point, and you had a bound that would be whatever number, like whatever representable number in the IEEE semantics, for instance, and that's not quite the real number that the inequality is from. And in that case, you might not be able to actually tell a computer about the actual number because it's not representable. And so that would be one form of imprecision where you just cannot talk about the actual number that you want to talk about in a computer. But here I'm not talking about that. I'm really talking about rather the fact that the rule itself does not give us as much information about x as it could, and it's not because of the value of the number that we can represent, but it's really because there are other numbers, and there's like even the assertion of an inequality is not quite necessarily the. It could give us also an inequality that says x is greater than 41, and I would not quite be happy with that because it doesn't tell me that x is. Oh, sorry.
But this is making some assumptions of context.
Mm-hmm.
So, for example,
Of course.
let's say the context.
Well, let's. Why don't we reserve that to the end, and we can get into any sort of additional questions then.
Okay. Yeah, this might get clarified a little bit in the next also example.
23 was a threshold, a critical threshold of the system. That's all the precision you need. Sorry, that took me into the setting.
Yeah, okay. Let's do that. So, for instance, so there are two ways of sort of deriving these rules, and one way is to sort of start from what we would like, what we expect to know after a statement runs, and figure out what should be the precondition that holds before, so that what is at the end is true. So, for instance, if you had to derive that after running the statement, x should be equal to 23 and b should be true, what do you think the precondition for that should be, given that x is going to receive this expression's value? So it seems like this would not update b, so if we know at the end that b is true, we should probably already know that it's true before we run the statement. And then if x is to become 23 and it's going to receive this value, surely this expression should already, before we run the statement, be equal to 23, right? That's the only way that this is going to work. So somehow it seems that for this to be true, the precondition will have to be at least contain that this expression in red will result to 23, and that whatever else was in this post condition that doesn't mention x also is already true. So somehow this gives us a hint as to what the rule should be for an assignment, for an arbitrary sort of post condition p of the variable x. Well, the only way that it's going to be true is that the proposition was already true as long as whenever it mentions x, you replace that x that was mentioned by the expression 6 times y minus 2. And somehow you should be able to convince yourself that if you take p and every time you see an x, you replace it with 6 times y minus 2 here, for instance, then if that entire proposition is true before you run the statement, surely after you run the statement, the proposition will be true when it talks about x, since x received that value that you replaced in. So somehow we can play this trick where we substitute the right-hand side for x in the proposition that should be true at the end, and that gives us what the precondition should be. And so the way we write this in this paper, okay, so first, yeah, we're going to need to, I'm going to write certain things like this that are going to be axioms, and the idea is that this bar says at the top what we need to know, and at the bottom what we can deduce from it. And an axiom is something that we're going to take for granted, so it's going to say, without any sort of precondition, we will be able to deduce this. And then rules will be something else where there are a bunch of conditions at the top. So for instance, here I have two conditions. Usually they'll be spaced enough that you can sort of see which ones are different. And a rule says that, oh, if you're able to prove all the things at the top, you should be able to deduce the thing at the bottom. And so the first axiom that Floyd-Hoare sets in this paper is this axiom of assignment that says without any sort of precondition, I should be able to deduce. So I would read this word backwards from the right. If I want to know that some property p is true after I put the value e in the variable x, surely it should be a case that before I run the statement, that property p was true when every time I see x in that property, I replace it with the entire expression. So I don't know if this is confusing or not. It's a little confusing at first, but with the example, you should get a feeling for why this is working. But yeah, really, it's sort of cheating by saying, oh, well, whatever the property is for x, since x received e, well, as long as the property was true for e, it will be true for x, since x received e. But so you see that, yeah, it lets us really go backwards, where like if we know what we want to try to prove, we know what needs to be true at the beginning. So what do you have next? Yeah, let's have this example. So I can do the swap example again, But given the way that rule was working, I should rather work from the end of the program and work my way backwards using this axiom. So at the end, I wanted to prove that x had received this y0 somehow, and that y had received this x0. So this rule tells me, well, if it's only going to be true when I go backward, if every time I see y in this rule, I replace it with y minus x, and this is what should be true, before. So, I guess it's a little ugly, I don't know why. Yeah, I know I did that, but, so I just replaced the y on the last line with y minus x, and now I would have to prove that at this point of the program, this formula is true. And if I keep working up this way, now I replace x in this formula by y minus x, and it gives me this, which is pretty ugly. But you see that, sorry, every time you see this check mark, it means and. It's almost only going to be and in this entire presentation, so every time you see a check mark, it just means and. So here I'm saying, well, for this to be true, it needs to be the case that y minus x at this moment in time was equal to y0, and this entire expression was equal to x0. So now later on, I'll give a rule that lets me also cancel things that arithmetically cancel out. So this y minus x should just cancel out to x. I don't know if you see it. Y minus 1 will cancel, and the minus x will become x. And I can keep propagating this up. Now I need to replace every instance of y with x plus y, and I did it. There's another cancellation that's going to happen, and eventually I'm going to end up with this, which says that this will only be true at the end if at the beginning y was equal to y0 and x was equal to x0. So it's sort of the same proof I did earlier, except this time we sort of propagated backwards from the end, knowing what we wanted to be true at the end and figuring out what had to be true at the beginning. So the reason why I did it this way backwards is because, again, the rule that I gave you for assignments sort of tells me from the post-condition what the precondition should be. And in a couple minutes, I'll go into another way to do this reasoning forward. But in the meantime, what led me sort of like keep doing this reasoning throughout the program is there are a bunch of rules that I've implicitly been using. And so in the paper, he makes explicit those rules for sort of reasoning compositionally about this program, being able to take apart instruction by instruction the pre and post condition for each instruction, and being able to link them together in a way that I've made very implicit here when I did it on the board. So let's see what those rules should be. So what he wants is some way of, I already said this basically, but we need some way of decompose this program. And so the first rule to decompose a program is to be able to decompose a sequence of statements. And so that's the rule he gives. And so this rule says that if you have a sequence of 2 statements and you want to prove some relationship between what you know before and after you run this sequence of 2 statements, well, you should prove 2 things. You should prove that from the precondition after running the first statement, there exists some R that it seems like it's coming out of nowhere, that is true, some sort of intermediate property that is true. And from that intermediate property that is true, if you run the statement S2, you should fall back on your feet and end up with the property Q. And somehow you should convince yourself that if it is true that when I start in a state that satisfies P, if I run S1, I end up in a state that satisfies R. And if it is true that starting from a state that satisfies R and running S2 gives a state that satisfies Q, surely running the 2 in immediate sequence should give me from a state that satisfies P all the way to a state that satisfies Q. So that's how we break up programs, by breaking them up at each semicolon in some sense. And then we have these sub-proofs to prove. But we sort of have to guess what this R is in the middle. Or, not necessarily. Maybe the rule for S2 might give us Q from R, R from Q. Or maybe the rule from S1 will give us R from P. But there's another problem in that it's not very compositional, because this R seems like it has to be the same. And how likely is it that the post condition of the first statement is going to be exactly the precondition of the second statement, when the post and preconditions are, we've seen there are sometimes like arbitrary arithmetic expressions or relationships. It might not be the case that we have exactly the same R, right? So we can also want to have a way of connect 2 statements, even though they don't really match up in their specification, as long as somehow the post-condition of the first one would imply the precondition of the second one. So we also want to have this rule that lets us sort of relax this rule a little bit. And that's why it also gives two rules of consequence. And so they might look a little weird at the beginning. So one says that to prove PSQ, you can prove PSR. So you can prove that after running S from the state P, you end up not in Q, but in some other property R, as long as the property R implies a property Q. In some sense, we say that it weakens the post condition because R in some sense is something, actually, did I get that wrong? Oh, I guess, yeah, it's always weird depending on if you read the rule like from the top to bottom or from the bottom to top. But in some sense, if you read it from top to bottom, then R gets weakened into Q because Q is a less, since R implies Q, Q might be something that's less tight than R, that's less precise. For instance, R might be that X is equal to 20, but then the Q was just that X was greater than 0, for instance. Yeah.
In the paper, instead of using the double arrow, he uses this.
Yeah, so there's a bunch of different notations that I've also updated. Indeed, in the paper, so first, instead of writing those vertically...
It's better. It's better.
Yeah, instead of writing them vertically, he writes them horizontally and using this turnstile symbol. But since then, we've changed the way we use those, and we use this to mean rules, and then the turnstile is often used within a line of a rule to mean something slightly different, that the system is able to prove this rule within itself. And then second, I changed this inclusion into this implies arrow, implication. That's so, yeah, I guess mathematicians, especially back then, used to represent implication as sort of the set theoretic inclusion of the set of properties. And I don't know, some people are happier with one or two, but nowadays logicians tend to use more of this implication symbol to not necessarily think in terms of set or like sort of make the distinction more crisp. But yeah, they're supposed to be the same thing.
I just wanted to clarify for the people following along with the home edition.
Is there a name for this notation versus the older notation?
It doesn't really have.
Or is there a field that's kind of like said that?
I mean, those are called, yeah, those are. There's something we call sequence from sequent calculus. That is very related to this, but this I think how do we call those?
Or what field would this notation?
Oh, this is used a lot in logic in general, but also in logic applied to programming languages a lot. So that's how.
Logic in terms of computer science versus
computer logic
versus philosophy.
Oh yes, computer. Actually, well, the line is sometimes a little unclear between the two, but I would say this is mostly used in mathematical logic more than philosophical logic, even though sometimes people are blurring the line between the two with certain things that are called modal logic.
I don't see this in the field of philosophy at all.
In some fields of philosophy where they do either like meta-theoretic reasoning or they question different notions of truth, they might use this in some sort of way as a way to derive formally notions of truth, but then in some other fields of philosophy, this would just completely not really be. So most likely not, but sometimes some people might use this because this is a very, very graphical way of representing formal systems that have those rules that are very precise.
A textual way.
Textual, but it ends up being very two-dimensional as well as it's graphical, even though, yeah, it's still very textual. You'll see later I'm going to write a derivation that starts becoming a little more two-dimensional in some sense. But yeah. Yeah, I don't have a better word than axioms and rules for those. I'll look it up later. Maybe I can come back to you. So the second rule to split apart those things would be, so here I worked on the right side. I changed this Q into an R, and sometimes you might want to also work on your left side, on your precondition. And there's a similar rule that says, well, if from a precondition P you could deduce a precondition R, then and if from R running the statement S give you Q, well then from P surely running the statement S will give you Q because P will imply R, and because the way the logic is set up, implication in the logic is gonna work for you. So this is called strengthening the precondition. And so now I'm going to show you how these two rules with the previous rule, so let's go back a little bit. There was this rule for composition that had this problem where you had the same R, but now using these two rules, we can build this derivation. So this is again the rule of composition that I had a little problem with. Now I can use the post-condition rule on the left to say, well, instead of having to prove R, I'm going to prove some A that implies R. And now on the right, I'm going to say, well, instead of proving R, I'm going to prove that R implies some other B, and that B is enough to prove that the statement 2 satisfies Q. And now, if you hide away the implementation details of how these rules were derived, at the top, we just had that P after S1 needs to produce some property A, and A must imply R, but R must imply B, so really A must imply B, because the R was actually not fixed. We could have picked any R we wanted, and so we can just pick, you can consider that if you pick R to be A or R to be B, either way you're going to be able to just reduce this to proving that A implies B. And so then if I just hide away all those details, now combining all these rules, I'm able to prove this more lenient rule that says that to prove that the sequence of two statements gets us from a state that satisfies P to a state that satisfies Q, I just need to pick up a proper A and B and verify that S1 from P gives me A, that S2 from B gives me Q, and that A implies B. And so in some sense, the way this is more compositional is that now you might get some specification from S1 from someone, and you might get some specification from S2 from someone else, and they never had to agree on the middle ground. But as long as you prove that whatever A guarantees is enough to verify whatever B wants as a precondition, then you should be able to chain these two programs together in sequence and go from the precondition of S1 to the postcondition of S2. And that's what I've been doing implicitly when I've been applying the rule of assignment multiple times through the program earlier. I was really just sort of applying this rule, and every time when I did simplifications, I was using the fact that if there's an implication, I can just replace a postcondition with what it implies. And so this mathematical simplification in a very formal system, you sort of have to actually say, oh, I'm doing this because I'm applying this consequence rule and I'm reinforcing or weakening this condition. So let's see, what do I have next? So now, yeah, remember when I was, so I'm going to talk about this reasoning backward and forward. Remember when I gave you the axiom of assignment, I told you, well, if you know that at the end you want, I guess I changed it to Q to hold, and you've been assigning E into X, then it had to be the case that before the assignment, Q was already holding, but where you replace E by X by E. So sorry, I also never said that the notation with the square braces and the left arrow just means that this is the same sort of expression as Q, except that every time that I see an X in it, I replace the X with E. I sort of implicitly explained that with the example, but that's what this notation means. And so remember I said this axiom, let us go backward. We started from the end of the program knowing what we want it to be true, and we were going all the way up to see what had to be true at the beginning so that this all worked out. Yes?
So what I find a little bit confusing about this particular sequence of instructions here is that there's no time that is actually occurring. Like, that's not one statement followed by a second statement followed by a third statement. It's saying that first statement is actually basically, it was already true before you even actually assigned E to X, that assigning E to X was okay.
Yeah, so yeah, whenever you read these triples, you really have to think what they say is that if before running the statement the first part was true, then if I run the statement, the bottom part will be true. I mean, I made them vertical here because eventually they're going to get bigger, but it's always in three parts. The precondition is whatever had to be true. Then there's a statement, that's the statement that we're considering, and then the postcondition tells us what's going to be true if the precondition was true, and we where to run the statement.
Right. So the point is actually that in the first precondition, there's not the old value of x in there. There's the potential value of e, and it's okay.
Yeah. They're really, they don't consider. Yeah, you should really think of x as a just a variable name, and even though you might think of it as a memory location that gets assigned, but I'm thinking really about the value of the variable x before was satisfying something. I run x equals e, and then whatever q, if q mentions, sorry, not q, well, I guess if the post condition mentions x, it mentions the value of x after executing the statement, whereas if the precondition mentions x, it means the value of x before executing the statement, even though it's the same. So there is some sort of, a bit of a temporal notion when you read this. There's things that hold for the state before execution of the program or statement. And then the second part of or like the third part of the triple really is about the state after execution. I don't know if it might get clearer the more we do examples of it. But so this rule that I showed you earlier, it had this sort of backward feeling to it, in that I told you, well, if we know q after execution, it had to be a case that this updated q was true before. But what if we know the precondition, and like this doesn't really tell us how to transform the precondition to obtain the postcondition? You might think that it's just reversing the arrow and replacing every instance of e from the precondition by x. But if you try a couple examples, you're going to realize that this is actually doesn't make any sense. And so also I told you that these triples were called Floyd-Hoare triples, and it's because Floyd was sort of deriving the exact same logic and setup independently. But except that Floyd worked all these axioms from the top to the bottom. And so he asked himself the opposite question, that is, if I know some property p before I run the statement, and again, p might mention x, the variable, and e, this expression, or any part of the expression, what do I know after I run this? And this is actually a little harder to answer, but maybe then the answer looks more intuitive once you've grokked it. But the answer, I don't know, I guess I could have you guess, but I don't think anyone can guess it. Like, it takes a while to guess it. So maybe I'm just going to show it and then like explain what it is and why it's so weird. The answer is this. So it's a little thing, and so it has three parts. It has this reverse e that says it exists some value, and I call this value x0 to give you the intuition that is, it's the value that x had before you run the state. So in the initial state. So we don't really know what it was, but there was some value that x had before running the statement. And what's true after the statement is that x is going to be equal to whatever e evaluated to, but with the caveat that if this e was mentioning x, well, the x at that point in time was equal to this old value of x, x0, right? So you have to replace every instance of x in that expression with x0, and that's what x after running will be equal to. And on top of that, you also know that, so there's an and the second part tells you that whatever p was holding before, well, it's still true, except that every time p was talking about x, he was talking about x before running the statement, right? So he was talking about really this x0, this old value of x. And so whatever p was mentioning about the old value of x is still true about the old value of x in some sense. So x has changed, but if you assume that somehow you know what this old value of x was, then these two things should be true. So I don't know if this is convincing enough, so I have an example to like reinforce why this is actually, what this actually does make sense.
Here you would read the dot as like a such that?
Such that, yeah. The dot is just, such that. So yeah, I guess that's all for. So let's, I think I have an example? Yeah, I have an example. So let's see, like if we knew that we were starting the state where x was 40, and y was 2, and b was 0, for instance. I put an arbitrary amount of things, some of which mention x, so that it's interesting. We see why some of the substitutions are interesting. So according to this rule, after I run the statement, this big thing should be true. So it tells me that there should exist some value of x that x had before, such that now, after running the statement, this new x is equal to the right part, in which I replace all occurrences of x with the old value of x. So that's what this line says. And then the second line, again, it's just I pick the entire the entire like assertion that was true before, that was supposedly true before I run the statement, and I put it again, and we're gonna have to replace every instance of x with this x0 that stands for the old value of x. And so what happens when I simplify this a little bit? Well, it tells me that this new x now should be equal to x0, the old x plus y. And you can see why. If I put in x plus y, surely after the fact it's equal to what it was before the fact plus y. And surely, since x was 40 before, well, since this x0 is supposed to represent that old x, surely x0 must be equal to 40, and y must still be equal to 2, and b must still be equal to 0. So again, this is assuming that the assignment here doesn't have any sort of pointer memory reference where actually x and y would be the same thing, which it couldn't be here given they have two different values. But assuming, yeah, right now I'm assuming that those assignments only modify the variable that's being mentioned, and I'm going to go back to that very quickly. And so, yeah, if you look at this, now it's a little funky, but it basically says that x is equal to 40 plus y, really, which is actually 40 plus 2 if you want to simplify that much. But that the new x is equal to the old x plus y, which is pretty dumb now that it's presented that way. Yeah, of course it's equal to the old x plus y. And of course the old x satisfies the old property for x. So that's all that this says, but that's how you formally define it. So again, you would just simplify to x equals 40 plus y is still equal to 2, b is still equal to 0, and you could even simplify x equals 42 given that you know y is 2. But yeah, so that gives us this sort of two modes of reasoning, and all the axioms can be also derived in both ways. In the forward way, so the forward way is you say, well, given an arbitrary sort of precondition, what is going to be the postcondition after each of the statements of your language? You can derive one such rule per class of statement in your language. And the backward reasoning approach is the opposite. We say, oh, if I want some fact to be true after running the statement, what should have been true before I run that statement? And so actually, I don't know how many years later, but probably like 5 or 10 years later, Dijkstra, I don't know how to pronounce his name, D-I-J-K-S-T-R-A. Dijkstra figured out that not only those things exist for all the operations of your language, but they can sort of be automatically derived and in such a way that they are the most precise you can get. So he introduced this concept of a weakest precondition to an operation, and that is if you want a postcondition to hold, you can automatically derive what's the minimal amount of knowledge you need to know before running that statement so that the postcondition will definitely hold. And conversely, there's this notion of a strongest postcondition. That is, if you know the set of facts that you know before running a statement, we can figure out the most informative set of facts that you will know after running that statement. So that is, both of these sort of like either propagate forward the maximal amount of information or propagate backward the minimum requirements for the program to hold. And it turned out that also these things can often, almost always, be derived automatically. The only really problem to derive this automatically is, first, turns out that when I presented, the Hoare's axiom for the assignment thing, it was actually the weakest precondition for the assignment rule. And when I presented Floyd's axiom assignment, the one that was going forward, it was actually giving us the strongest postcondition for the assignment rule. And so yeah, those were the sort of most precise rules that I was talking about earlier, in that every sort of other fact that you could derive, for instance, a strongest postcondition means that there is nothing else that you'll be able to prove about the state after that you wouldn't be able to derive from this postcondition. It contains all the facts that you could want, and I mean nothing more, obviously, because then there's not any other truth that's missing from this postcondition. Now the only problem with this deriving this automatically is loops. So let's talk about loops. I think in this paper he mentioned them a little bit. And so the problem with loops is that, so if you think about it, what is true after this loop ends? So I made sort of an arbitrary loop. So when I use this exclamation mark, it's for negation, Boolean negation. So assume there's a Boolean that tells you when you're done, and the loop keeps running until it's done, and it just keeps updating x with some function f on x, and it updates done with some predicate that tells you, given x, whether you're done or not. And you're trying to figure out, well, what's true at the end of this? And the problem is that, well, I guess it depends. If the loop runs 0 times because done was already false, then surely these two properties, whatever they were, they're still true. But then maybe the loop ran once, and then, well, probably the property on x must be maybe affected by the fact that we just assigned something into x. So maybe it's not true anymore. Maybe the property about y is still true because we're not modifying y in the loop. So maybe, I don't know, if you had to guess what's true at the end of the loop, well, surely the done variable must be, what is it? While not done. So while not done is true, we keep looping. So if we stop looping, not done must be false, so done must be true. So surely we should be able to say that, well, done must be true, and then we don't really know what happened to x. X has been maybe updated many times. Probably P2 of y is still true because the loop body doesn't seem to update y. But so what do we do with x? And so here the insight is that to deal with loops, what if I told you that there is some property that the f function preserves from its input to its output? And what if I told you that this property is true? Let's say that it's P1 here. So if I tell you that before we run this, I'm in a state where P1 of x is true, and I'm telling you that if you run f on an x such that P1 is true, it's going to give you back a result such that P1 is still true. Then surely, however many times I get into this loop, P1 keeps getting preserved even though I'm keeping updating x. And at the end I exit the loop, surely P1 is still true of x. So this notion is called an invariant of this loop. And the idea is that if we can exhibit such an invariant, then no matter whether we didn't run the loop or we ran it many times, if it held before the loop and it's preserved by the loop, it would have to still be true at the end of the loop. And so here's what the rule for this while statement looks like. It might be a little bit daunting, but what it says is that if you want to prove that some property I, I'm naming it I for invariant, gets preserved through a while execution, you would have to prove that executing the body of the loop in a state where I, this invariant, holds, and where, since we know that we entered the loop, we also can guarantee that the condition is true, C. Then if you can prove that running the statement preserves I, then you'll be able to prove that running this entire loop is actually going to give you back I at the end of the loop. And also at the end of the loop, since the loop terminated, you also get to know that C is finally now become false. The condition is false because if you went past this entire loop, it must be that the loop has exited. Again, this is assuming a language in which there's no sort of break statement or weird ways of exiting a loop without exiting the condition. In those languages, you'd have to change this rule to account for the fact that there are different ways to disrupt the control flow. But yeah, I'm assuming a simple language where a while loop just runs S and checks the condition again. That's the only way that it's going to stop looping is when C becomes false. Okay?
But we can never assume that's the case because there could be an error or there's
yeah, so again, those are done in a very how would I say that? Idealistic language that's very simple, and we keep building, and then but we can take into account more and more of those crazy language features such as
the real world things.
Yeah, I agree that the real world has them, but those are building blocks from which we can build more interesting control structures that include those disruptions of control flow, includes any sort of exception mechanisms, callbacks, continuation-based. But basically, we start from the basics and we keep building on top of those things. So in here, this language, the semantics of this language are such that this while loop does not have those features. It's a primitive while loop in some sense. And if you want to build a while loop that maybe contains exception, you'd have to build a language on top of this, and this rule would not hold in that language. And you'd have to build more like different rules. But yeah, I agree that this is not a realistic language, but it turns out that with those and like some more engineering effort, we can actually build and add more language features and build rules for those language features. And it's not easy at all, and that's why there's been lots of research since 1969 to make this happen, and it's still not quite, like, there's still not many great tools to do this. But we keep getting better and better, I think. And so speaking of those tools, so I just told you that a lot of these things can be derived automatically. And so the only problem with loops is finding this invariant is actually hard. It's not doable in some sort of automated way. And so up to now, we use just the human brain as the oracle for what the invariant of a loop is. But there actually is a tool that lets you automatically derive those things and tries to find those loop invariants. It was built by Microsoft. It's called Boogie, and you can try it online. Whoops. Well, I don't want to do that. I think I have it here. And they have a bunch of examples, and you can look at it. I'm not going to go read through it, but it's a somewhat more realistic language in that, for instance, it has some go-to statements, and it's able to reason about certain interesting properties of programs automatically, except with the caveat that you have to give invariants for loops, and you will verify that the invariants indeed are preserved, but it does not guess the invariants. There is also a lot of research on guessing invariants, and there are many different ways, and I don't know them all, but we're also getting better at guessing those invariants. Whoops. And now, oh, I'm actually already late. I was going to talk about something else, but it's going to take a while. I don't know, do we have like 10 more minutes, or do I stop?
Yeah.
Okay, if you want. So another problem that I've been really hiding under the rug for a while is, whoops, how do I get back here? Is pointers. Oh no, this thing is getting me stuck. No, I do not want to install anything.
The loop didn't finish.
Yeah, I was stuck in this loop. Okay, I'm back. No, I'm not back. Oh, I see why. So a problem that I hid under the rug this entire time is that I was using those variables that are actual sort of, you can think of them as like stack allocated variables. There's variables that are definitely in distinct parts of memory. They're not interacting with each other ever. And that's not how we program, right? Oftentimes we have a heap allocated memory, and we share different pointers to it, and all sorts of weird things happen. And so that was a problem for a while, is that we didn't really know how to deal with those. And so you can deal with those in this logic, but as we're going to see, it's not going to be pleasant at all. So the problem is, right, when I say, oh, x is equal to 0 and y is equal to 0, and I run this statement, then I can say, well, after this statement, x will be equal to 4, and y will be equal to 0. When I write this square bracket notation on the left, it means accessing the memory at address x. And when you'll see the same notation on the right, you'll be accessing the memory in read at the address. So here I'm saying I'm storing the number 4 at the address referenced by x. And so we might falsely convince ourselves that this is always true and that it will work out. But obviously, this tells me that x and y points to 0, but it doesn't really tell me that they have to be in this setup on the left. They could really be in this setup, where they both point to 0, but the same memory 0. And now, surely when I run this, it is not the case that x points to 4 and y points to 0, right? Actually, both x and y have been updated. And so this problem is called aliasing, and it's a problem that once you start having these memory allocated variables, and they may alias, that is, they may refer to the same actual memory area, block, region, cell, whatever you want to call it, address, then suddenly the assignment rule becomes a little weird, because it might have effects not only on the variable that you assign to, but on all the variables that are pointing at the same address.
So this is static pointers. Dynamic pointers for x and y. Part of the process is actually changing to where they're referring to.
Yeah,
which is iterating through an array. Is that coming up? Or?
It is coming up, actually, yeah. Those would be dynamic pointers, but this tells me that if statically I definitely know that x and y point to the value 0, and I run the statement, do I actually know that after running the statement they definitely point to 4 and 0? Well, I do not actually know that, because even though I knew they were pointing to A0, I don't really know if they're pointing to the same 0 or to different instances of 0. And so I'm not really able to make this claim. And so we're going to find a way to sort of reinforce those claims so that we can distinguish between those cases. And so the way to do that is to actually account for aliasing in those rules. And so you might think it's not that big a deal. Well, I'm going to say if before x was pointing to something and y was pointing to some y0, and in the memory referenced by x I put some variable v, surely I should convince myself that after this x will point to v, and then either one of these two things. So now this thing that looks a lot like a v, which is very unfortunate, in the center is actually an or. And it says one of these two things will be true. Either x was not equal to y in terms of addresses, and in that case I know that y will still point to the old value they was pointing to. There was no aliasing, and so this assignment could not have affected what y is pointing to. Or the two addresses were the same, and in that case then y will also point to the same variable v. But so this makes verification completely impossible to scale, because now in every rule you have to account for sort of all the memory and say, well, for all the memory that was pointed to by x, it's going to get influenced by this assignment. And for all the rest of the memory that was not aliasing with x, it's going to stay the same. And it's not a big deal when you have a small thing, but when you start having like a program that does something like, this is a linked list reversal. And so the way it works is that it uses temporary variable. So if you represent linked lists as sort of like two addresses that are consecutive in memory represents one cell, where the first address is whatever number, for instance, you have in the list, and the second cell is the pointer to the next element of the linked list. Then I can run this algorithm, and you would convince yourself that it sort of reverses this linked list. So assuming that I'm trying to reverse the linked list that is pointed to by I, so here the list would start with 0, 1, 2, 3 up to the end. And this is sort of like my null pointer, which I guess I call nil. Not very important why, but so if I run this thing, what it does is that it creates this temporary that points to whatever the next cell refers to. So it actually points to the next element in this linked list. Then it updates the next field of I to point to whatever this other linked list j points to. Then it makes j be equal to y, so j starts pointing to whatever I was pointing to, and I gets updated to point to the temporary variable, which was the next cell. And if I run this again, you'll see that the temporary grabs a reference to the next cell, then I points to j, which was the previous cell, and then j points to I, and then I points to t. But so it's a little crazy, because what is this loop invariant here? The loop invariant is kind of complicated. Basically, it is that every time we're at the end of a loop, or at the beginning of it, it is the case that I points to part of the original linked list, some sort of suffix of the original linked list. If you see, here it's the suffix 2 followed by 3. And then j points to the reversed prefix of the rest of the list in some sense. And so if you want to represent that in this logic without any help, you're going to have to write an invariant that looks kind of like this, where you're going to say, well, there's some alpha and beta prefix and suffix of the list, such that I points to this prefix and j points to the suffix. And if we sort of reverse the prefix and concatenate them, they're equal to the original list. But on top of having to know that, I also want to know that I and j are actually all the cells that they may refer to through the linked list are never the same cell, because if they are the same cell, then when I start updating I will break whatever I know about j, or when I start updating j, I will break whatever I know about I. And then I also want to know that all the data that's in the rest of the program that has nothing to do with this linked list has nothing to do with this linked list, so that I know that while I'm reversing this linked list, I'm not actually destroying some other data structure from the program that I don't even have any pointer to. So you start having to write these insane conjunctions of facts about the memory that are really unwieldy. And so the idea was to make this notion be part of the logic itself. And so later someone created something called separation logic. and it adds this other operator star that is kind of like AND, but it has an additional meaning in that in this logic, every assertion that is connected through this has some sort of footprint, and that means that whatever memory cells this assertion mentions are sort of held by this assertion, and when two assertions are connected with this star, they have to talk about this joint part of the memories. So even though the statement looks the same, when I use this star, it also implicitly means that all the cells that I points to are distinct from all the cells that the J points to. And so this, there's a bunch of rules associated to this operator, and this lets us like reason about those programs that deal with memory without having to manually write all those sort of like disjointness predicates, because they're embedded in some sense in the logic. So in this logic now, the assertions mean something else. Before, when I said x points to 0 and y points to 0, I really was just saying that. But when I write this thing at the bottom, I'm actually saying that x points to 0 and y points to 0, and there are different addresses. And alone, that's also this. When you mention something like that, it's also going to be saying that the whole memory that this assertion talks about is only the sort of like accumulation of the memory part that each assertion talks about. And so this assertion also guarantees that everything that is not referred to by x or y will be sort of like is not being mentioned by this assertion, and as a result, the rules will make sure that you get preservation of whatever is true of the rest of the memory for free by this logic. Yeah.
So could you summarize that asterisk is implying no side effects?
It depends what you mean by side effects, I think, because it's really saying that no, it's more saying it's for me it really means disjointness of the assertions, in that this assertion might talk about a memory location or area, and the other assertion might talk about another area. And if I'm able to prove that these statements are true with this connective, it means that the two memory that each statement talks about have to be disjoint.
So it means that any change to x will not affect y.
Yeah, exactly. So in that sense, maybe that's what I mean. There's no side effect from one region to the other region. There's no way that modifying anything in the footprint of the left statement is going to change properties that we know about the right part of the statement.
Okay, that makes sense, and it doesn't. It does not. I must have misunderstood, because I thought it was also implying that outside of the realm of x and y right there, that they can't affect any.
It also actually implies that. It also implies that.
That's what I was getting at.
Yeah. So there's two things. Yeah. So there's each sort of assertion has its own footprint, and they may only affect things within their footprint. And so the footprint of a points to assertion is just the address that it talks about. And so, yeah, there's also this notion that an assertion like x points to 0 says that there is a memory location x, and its value is equal to 0. And this assertion only cares about x and not about the rest of the world. And y also only cares about the y and not the rest of the world. And so if we have an implication that just mentions x and y, it also implicitly means that every other memory location that do not alias with x or y must be untouched by whatever the statement is. So that might be clear when I give a couple examples. So again, this was false before, but no, oh, sorry, this time I used star x, but star x is again the square braces x. I was supposed to change that. So it wasn't true that if before x pointed to 0 and y pointed to 0 non-disjointly, then the right-hand side would be true. But now the bottom rule is actually derivable in the system. If x and y both point to 0 in a disjoint way, then updating x will guaranteedly update x and guaranteedly not update y, because they are guaranteed by the system to be different parts of the memory. And so we can keep track of sort of those parts of the memory, and whenever there is or there isn't aliasing, to have like more interesting rules in the system. And so, for instance, you could prove that this program was actually implementing linked list reversal, which I'm not going to do. But the idea would be to use this invariant and to sort of like, you would have to go through this thing either forward or backward, and prove that from knowing that I is true and that the capital I is true and the small I is not the null pointer, then you would be able to prove that at the end of the loop, the invariant is still true. And note that a loop invariant may be broken as we go through the loop. So I definitely think this one will be broken in between. But the only thing you need to prove that a loop sort of like keeps propagating an invariant, like keeps making it true, is to prove that the entire body, after you've done running it, satisfies it. So you don't have, it's not a problem if locally, temporally, really, the code breaks the invariant, as long as before you end up at the end of the loop, it restores it. And so again, that's part of there's no way to break out of this loop except coming all the way at the end, re-evaluating the condition, and then leaving. So it would not, you'd have to do something very different if there are other ways to exit this loop. But so then I guess this separation logic gives us this tight software of describing memory and disjointness in memory. And so for instance, this will not be true. And the reason why this will not be true is that he was saying that in the state before we run this, there was a memory region called X, and there was a memory region called Y, and they were disjoint, and they were both equal to 0, and then we did an assignment. And at the end, I should not be able to forget that there was a memory region called Y, because it would sort of be forgetting about memory. So in some sense, this logic keeps track of resources and of memory allocation in some sense. You can also use it to keep track of things that are not quite memory allocation, but more sort of ownership of data structures or things like that. So it led to like a bunch of different areas that deal with that. Oh yeah.
So would this be invalid or imprecise?
Oh, it would be invalid this time. It would be invalid because this logic does not let you forget that there was a memory location called Y that was disjoint from X and disjoint from the rest of the world. So somehow, implicitly, it does always end this statement is disjoint from the rest of the world, and you have to keep track of the resources that are known about. Yeah.
Are you saying that it's incomplete or wrong?
So I would not say incomplete. It is incomplete means something else in logic. So
I guess
is it a subset of correctness?
no.
So no, here I would say that this rule is invalid in that it is not accepted by the formal system. So you won't be able to prove that this is true. It will, if you try to derive this as a truth, you'll probably end up, if you go forward, you're going to end up with the knowledge that x points to 4 and y points to 0, and there is no rule in the system that lets you forget that y points to 0. When it's being used with this star, because the system is built so that you never forget facts about memory. You may forget that y points to 0. You may forget what y points to, but you may not forget that there is a memory location y that exists that is allocated.
Isn't that imprecise?
So it is imprecise. So here, like, there's two things. So if at the end you would say there exists a y that points to and question mark, I don't know what, that would be an imprecise statement, but a valid one in this logic. But if you entirely remove the existence of y from the picture, then this is invalid. The system will not let you forget about the existence of a memory location referred to by y. Because in some sense, it's kind of like capturing the idea that you should not be able to lose pointers to memory without freeing it. So the only way you're going to be able to get rid of a y0 is by using a free statement, for instance, that lets you free the memory, and you're going to have an axiom in the system that says free is one of the only operations that lets you forget about a memory part. But yeah, the way this logic is set up is that...
So we're missing one of two things.
Mm-hmm.
One could be in the middle, something that deallocates y.
Yeah.
Or if it's not deallocates it, to account for it at the conclusion.
Exactly. If it is not deallocated, somewhere in the conclusion, it must be accounted for. Yeah. And we might forget the exact value that it points to, the 0. We might say, oh, there exists a y that points to an unknown, or there exists a y that points to a value such that it's less than 3. But we cannot completely forget about y in this kind of logic.
Well, what if part of the process confounds x and y so that they do overlap? So for example, let's say we have part of what's being done, the process, that
Mhm.
y's pointer is updated so that it becomes an alias of x.
So in that case, this assignment where x becomes an alias for y,
Or go the other way around.
or the other way around. So there is an instruction that is going to create this aliasing, and this instruction, there's a couple things. Either if it sort of updates x and replaces it with, how would I explain that?
So let's say we updated x with 4, and then
Yep.
right after that we updated the address or the pointer value of y to point so that it's the same as x. So x and y now point to the same.
So
the same 4.
yeah, so if you had an instruction that updates the value of the address that x refers to be something that y, this instruction would either it's the rule that applies to it, would have to account for either the fact that it's sort of like losing or like merging two memory cells together, or otherwise it wouldn't be really admissible. So you would have to, if there's a rule that allows you to sort of forget about some memory cell, it would have in its specification to say that. So usually the only rule such that it does that we allow is the rule for the freeing operation, and so we don't really allow in
That's
those.
not true, because let's say that
Just
wherever y is pointing.
In the interest of time, we
Sorry.
should probably move on.
Oh
We
yeah,
can
I mean,
reserve that to the end.
I'm basically at the end of the talk. I just went to it. So it might be weird because this doesn't tell you how to run this in an arbitrary, but in a memory that has more than x and y, if there are other parts of the memory. But so there's a rule that lets you sort of say that, if you're able to prove some statement in this logic, that some statement S from a state that satisfies P gives you a state that satisfies Q, then for any sort of arbitrary other part of the memory that you can think about, you should be able to derive that you can still run S in a state where P exists and R exists but are disjoint. Again, this enforces digital runniness, and it says that if there is another part of the memory that is not mentioned by P at all, that doesn't interact with P, then you can still run S, and the memory you're going to get is going to be also dividable in a part that satisfies Q, and the other part will still satisfy R. So in some sense, it tells you that you may run this in an arbitrary context as long as they don't overlap, and then you get the guarantee that you're not going to mess with that other part. It's still going to satisfy the same R sort of property that it had, and you get to know that the part of the memory that you interacted with is still disjoint and still satisfies whatever update from P to Q S made happen. And so yeah, the only things I had later on is that there's a lot more about this. So separation logic is just one of those sort of logics that encode more than just sort of the usual mathematical logic that we use. So here it encodes this sort of like resource tracking and memory location tracking. It's being used, for instance, if you know about Rust, there's this notion of ownership of regions of memory or like data structures and borrowing of this ownership. And it's basically a very similar idea of having a logic that lets you keep track of what pointers may talk about what data structures and whether things.
That meetup is next week.
Oh, okay. Oh yeah, there was meetup. And then there's also a lot of things. So this was more about imperative programming, and you might wonder, what about functional programming? And it turns out that we can actually use this work in functional programming. So for regular functional programming, you can actually just reason about it in a very mathematical way, because it doesn't really have a notion of side effects if you just take a pure fragment. But if you want to talk about functional programming with effects that are often using monads to sort of like talk about side effects, full computation in a very safe way, you can actually implement all of these rules that I've talked about within a type theory, so within a type system. And then there's a lot of work on that so that you can actually do these proofs in a functional language at the type system level. And there's work nowadays on mixing dependent types, which is these crazy type systems, with linear types, so that things kind of like this separation logic I talk about, where you can talk about resources and whether they are always used at most once, whether they may be shared or may not be shared, and things like that. And then there's a lot of people who try to extend this styles of logic that usually we refer to as Hoare logics, to concurrent programming, to probabilistic programming, in which case you have to change almost all these rules to account for whatever may happen in a concurrent setting when even if you didn't change variable, if it was shared with another thread, it might have changed without you noticing it, so you have to account for that. In a probabilistic setting, you might have to account for the fact that all the assertions are not precise in some sense, but have more like of a maybe a distribution of knowledge about their values rather than an exact value.
Would it be fair to say that in a highly parallel system, that this all falls apart? That this all falls apart?
Oh, yeah. So in a very parallel system with shared memory, everything that is shared falls apart unless you reason. Yeah, then you have to start reasoning at the entire system level. If there are invariants that are held by the fact that different agents in the system act according to a protocol, then you might be able to put these rules about the protocol within your logic as axioms to say, oh, even though this memory is shared, if I know that I'm in this state, the system should ensure the fact that this will only get updated that way. But yeah, then if you have a very parallel system, you have to start accounting for the rules of the parallel system in some way. And yeah, this definitely falls apart as like without any help. You also have to add axioms that describe what is expected of the entire sort of ecosystem and what is the protocol that is being followed by each part of the distributed system in some sense.
And I imagine this also falls apart in a data flow, where data isn't organized in terms of being placed in locations and addresses, but they're literally flowing through a data flow.
It doesn't fall apart, it just becomes much more difficult to think about.
I mean, fall apart meaning it's no longer useful to think about in that terms.
Yeah, it might become very ugly. But again, yeah, for instance, the work in concurrence is also trying to deal with these issues of like, whenever memory is no longer something that you have a complete control over between each instruction, but when you take into account the fact that there are other external things that may change the properties that you know about something.
Just kind of putting in bounds the areas that this is useful and not practical. Conventional single core CPUs, this looks very useful.
Yep.
FPGAs, it looks not very.
But this is without context, really. That's a whole other conversation.
Well, in a massively parallel shared memory.
Well, you might still be able to reason about those if you I mean, yeah, you would have to take into account whatever. So I guess, yeah, if there's a notion of shared memory, or if there's a notion of what could happen in FPGA. I guess I mean, there's still a notion of
whatever the heck you want.
Each CPU is following its control flow. Okay. I guess if
well,
you have. Oh, I see. FPGA, we're just thinking about the actual like sort of what do you call this circuit.
Not organized as a central processing unit running in sequential instructions.
Yeah. Well, it's
yeah, that's a very different at that point.
Why don't we wrap it up and then we can discuss further after.
If I may ask one last question.
Yeah, I mean that's the end of where I was going anyway. Yeah.
What with anything that takes a lot of effort to get wrapped around your mind, you got to ask the question: so what? What is this good for? Where does it pay off? What are the real strengths? What's the advantages of knowing about this? Or on the other end, is it just mathematical masturbation that we could just move on?
Oh, so it isn't. Yeah. So it might look like just mathematical masturbation. In practice, for instance, Microsoft has used this technique to build an automatic driver verifier. It doesn't verify what the driver does, but it verifies that driver. So basically, drivers are written by whatever merchant of device does, and it's sort of like code that the Windows kernel, for instance, is going to jump into and execute. And they would hope that this driver does not hang, because then that's when you get a blue screen of death, where you call into some. So, and it's not code that Microsoft has under control. It's code that whoever ships the devices or ships with it. And so they wanted to have a way to guarantee that those things, to have an automated way of knowing that this thing will not hang. And using this technique, they made a tool, I forget the name of it, that automatically figures out whether, automatically sometimes figures out whether something will hang or will not hang, and if it cannot automatically derive it, lets you know why it's stuck, and given that then you sort of look at it and give invariants for those kind of looping constructs, then it helps them in verifying that those drivers are not going to hang your system. Are there other applications? So, it's being used in this Rust type system, for instance.
Does anybody subscribe to communications? Are you ACM members, anybody? The latest communications of the ACM has an article about using formal methods for medical radiation systems.
Oh yeah, actually no, the people, is it at University of Washington?
Yes.
Yeah, so I know the people who use this. So yeah, they're using it to prove that, so there was this famous incident of the Tirac-25, which was a radiation machine that had this weird UI bug where basically there could be a sequence of operations that you would do that would keep the laser, whatever I don't want to call that, lasering, even though from a UI point of view, it looked as if you had stopped it. And there was, I think, a handful of people who got lethal doses of radiation. And so there's a group at UW, at University of Washington, who works on verifying parts of this software using this technique. What else do I know about? I've been using it personally to verify certain small systems, sort of verify a system that lets you write little systems that have multiple agents that interact with each other but with no shared memory. So it's not quite a parallel or distributed program. It's more, how do we call that? A reflexive system, we called it. It still needs, basically it needs to be integrated into languages that people use to get used. And actually, it's being integrated, for instance, in the Haskell language. There is an extension that's being built by people at my team called Liquid Haskell that lets you automatically derive certain interesting properties about your programs. This time it's in a functional setting, so it's a little simpler than what I've showed. But they use an SMT solver to sort of automatically prove that, I don't know, you don't have accesses of arrays out of bounds, because you can keep track of all the ranges of all the values and make sure that you never have an out of index, or what do we call that, error in accessing ranges. So it's still, it still needs work to be practical and usable in any arbitrary language.
It's had decades to mature.
Oh yeah, but
it's had decades to show its value.
All right. Well, thank you very much.
I've also had decades too.
We really appreciate your coming.
Yeah, thank you.
Thank you.
Awesome job on the presentation.